Okay, so it's 5:30. I'm just gonna get started. Let's pick up a level. Hi, Seth. All right. So today is gonna be probably my final lecture this semester. So I figured I kind of want to cover optimization techniques. So these are just ways to improve the training of your neural network. And again, I'm not really covering any like new fancy deep learning architecture, right? And again, hopefully some of this should be review, some of this should be new. So yeah, let's just get started. Okay. So again, the general question that I'm trying to ask today is how can we just improve training a generic neural network, right? It could be a CNN, but for today I'm talking about feed forward neural network. So some problems that we've kind of encountered throughout the past year is I'm sure we're all familiar with overfitting and underfitting, right? So when your model memorizes the data versus it fails to really generalize to the data, those covered vanishing and splitting gradient, which as you guys know is when during backpropagation while you're calculating gradients. If too many of your model weights are big, right, your gradient becomes huge. That therefore your model weights update in a massive direction. Conversely, with vanishing gradients, if your weights are too small, well, in that case, your approaches zero, right? And the cursive dimensionality, I think, is something we covered all the way in like lecture 2 or 3. And that I'm going to get into it at the end of today's lecture, but that's really just about as the number of dimensions in your input increase, the number of dimensions in your feature space. So in this case, our feature space is just like 3-dimensional. It becomes significantly harder to optimize your model. Okay, first, let's just do a quick review of overfitting and underfitting, right? So as you know, overfitting is when the model memorizes the training data. So normally this would be great, right? Like you want your model to kind of learn the distribution of your data. The problem is that the training data is not a perfect representation of the entire data distribution, right? The training data has noise, right? As you kind of see in this case down here, right? So again, I'm sampling like triangles and circles, right? And you can see that the true distribution of circles versus triangles is a little bit smoother, right? So kind of the good classifier, right? Overfitting though is capturing all those like precise like noise, like all those edges and divots and stuff that aren't really there in the smoother true distribution, but instead exists only in this data set, right? And of course, underfitting is when you just completely fail to really learn the key trends of your data. Okay, so I'm just gonna do often. So I've been doing some like machine learning prep and stuff, right? And so a common question that you're gonna be asked is to describe like the bias versus variance trade-off when training your model, right? And so again, this is all stuff we've seen before, just kind of explain in statistical terms, right? So again, as I was saying, right, imagine like your underlying distribution, right, is like, your data follows the cosine, right? The cosine function, right? And if I wanted to train a model to fit to this cosine function, right? Well, I would maybe sample some data points from it, right? Now, again, in real life, right, if I were to observe like this cosine function in nature, well, whenever I sample stuff from it, I would probably get a little bit of noise, right? So you can see that this data set I assemble from sampling from the cosine function has a bit of noise. It's not completely perfect, right? And again, for this really simple example, right, you can be like, hey, I can just like take numbers on this line, but you can imagine when this true distribution is not known, right? And you do just try to assemble a data set just from observation, then you will certainly have noise, right? Okay, so let's kind of define bias and variance in like through an example, right? So before I get to explain what those are, I know there's a lot going on in this slide, right? So let's take a look at like what our model is. So I'm going to call our model f hat for the next couple slides. So let our model just be a linear model, right? Y equals mx plus b, y is wx in this case, and we want to like tweak w and b in such a way that the model like the line fits to this cosine function. As you can see, like the cosine function in the line, like the line literally cannot fit to the cosine function, right? It's a line. It's got no curves, right? Regardless, we do our best to fit, right? So f hat underscore 1 is just trying to fit the model to the blue data set. 2 is fitting to the red, so on and so forth, right? As you can see, it doesn't do very good. So the expectation, so E underscore D of F hat is basically the average over all of the different models, right? So for example, at this data point, this is the average for each of the F hats. So this so again, this is the expectation, which is the average across all models. Does that kind of make sense what the expectation is?
Wait, so like,
Yeah.
when you say all models, like, why would you want
All-
the expectation of like 3 separate models?
Yeah, I'm about to get to that.
Okay.
Yeah, but does it kind of make sense that this is the expectation of like,
Yeah,
okay. So again, if you had 100 data sets, we take the expectation over those 100. In this case, we only have 3. So, right, what we want to do is measure how good our model is, right? So there's 2 metrics that we kind of go to for doing that. One is called bias and the other one is called variance. So bias takes this average model. Again, this average model is kind of representative of, on average, how does our model do on this data distribution, right? So we take that average model and subtract it from the known data distribution, right? And so when I say subtract, what does that mean? There's a lot of different ways we can calculate the subtraction. In this case, we could just take the integral of the difference, right? So at every single point, sum the difference. If that makes sense, right? Of course, when the data distribution isn't known, we have to get creative in different ways. But for now, the data distribution is known. So as you can see, the difference in model outputs between our averaged linear classifier and the true distribution is pretty significant, right?
wait, so the f of x, sorry, I'm gonna miss this when I was in the bathroom.
No,
The
you're
f of
totally good.
x, is that one data set that's being used? Like, what does that mean by true distribution compared to like the different data sets that each f hat is being trained on?
Yeah, so F just refers to like our model in this case, right? So the model in our case only has one input, like one input point. So that would be X. So F of X would be the prediction for data point X. So F hat 1 of X would be the model trained only on these blue dots.
Okay.
So one data set. F hat 2 would be on the red point.
So
So
all the data
yeah.
sets are sampled for the same distribution.
Exactly.
Okay, that's tough.
Right. In a perfect world, right? All these sample data sets would be identical to each other, or like roughly identical, right? In practice, there's always a little bit of epsilon from it. Like even if you were to sample like points from the sine function on your computers, it would still have like 1 to the like e to the minus 100 like bit of noise, right? Just because of the sort of floating point errors and stuff, right?
Yeah.
Like you can never perfectly sample, right? From a data set. Does that answer your question?
Yeah.
Okay. Yeah. And you're good on what like the average of
Yes.
F is. Okay, perfect. And so again, bias just measures this difference between the average performance and the actual distribution. So again, the linear classifier is very bad on bias for this specific distribution. Variance, on the other hand, compares the average performance. So again, E of D, expectation of F, compared to all of the other F hats, right? So we compare the averaged model to each of the individual trained models. And then we take their difference, square it, and take the expectation of the square difference. So in other words, right, if these 2 models are very similar, right, the difference would be very small, and therefore the variance would be extremely low, right? So we would say that this linear classifier model on this specific data distribution has high bias, but low variance, right? So what we can infer from that is, okay, our model like has a bunch of built-in error, right? Like most of our points are going to be wrong. However, at the very least, even if like we're going to be very consistent, right? So I can sample whatever I want from this data set, and I can expect the linear classifier to be roughly the same each time, right? I can add a point here from the data distribution. I could add a point here. It won't like mess up the model too much. So on the flip side, let's let F hat be a neural network, right? With as many parameters and weights as you want, right? So once again, we have the exact same data set. And as you can see, a neural network can fit to this data distribution extremely well, right? So well that it fits to each of the exact points, right? And again, I'm not showing the neural network, but just conceptually, you can understand that neural network can fit to something this simple very easily, right? Okay, so again, the average of each of the F hats, right, is pretty much the sine function. It looks really good, right? So in this case, the difference between the averaged F and the true distribution, the cosine function, is pretty much zero. It's like super low. The bias is extremely low. There is no built-in like there's no built-in bias or built-in error from the model. Like the model's in theory capable of representing this. However, variance is a little bit different, right? Again, variance compares the difference between the averaged model and each of the individual distributions. Well, you can see that because the model ended up overfitting, right? It ended up precisely matching each of the data distributions. The average model kind of differs a lot based off the data set, or the F hat differs a lot based off of the data set, right? So in other words, if I were to give it, like if I were to sample a completely new data set, D4, right? Yellow points, right? We would expect this new F4 model to kind of deviate from this averaged one, right? And in contrast, no matter what I kind of sample from my data set with the linear classifier, I can always expect it to be pretty much all of them to be very similar to each other. I can't say the same thing about the neural network.
Can you explain why that's like a bad thing necessarily? That
Yeah.
There's having.
Again, yeah, good question. So again, I don't really like, at the end of the day, I don't want to learn this data, like this data set. I want to learn this entire data distribution, right? And so the problem then arises that each of these data sets, right, kind of represents this bigger true data distribution, right? If the model ends up like behaving differently for each of the data sets, that means like we can't really expect it to behave consistently, right?
So it hasn't really learned the distribution.
Um, Not to that extent, but it's more so that like, oh, if I just like add a couple more points, the model will like change a lot.
Okay.
Like completely fluctuate. If that makes sense.
Yeah.
Okay. Yeah. So again, like you can express the entire error of your model in terms of squaring the bias plus the variance and then plus the reducible noise. And irreducible noise is that built-in error we get from sampling. So again, like it's the true distribution fx, like for a given sample x, plus some epsilon noise, right? And again, if we were to sample like stuff from the cosine function on our computers, epsilon would be extremely, extremely low, right? But it would still be there, right? In other words, our error could always we'll always have this kind of built-in irreducible noise error that we can't do anything about. But yeah, okay. So I know there's a lot on this slide, but just to recap, right? High bias often happens, as we saw, with simpler models with fewer parameters, right? If you don't have enough parameters, you can't really fit to the distribution of your data, as you can see here, right? High variance happens when you have really complex models that can perfectly capture, like really closely capture all the intricacies of your data set, right? Remember, we don't want to learn the data set, we want to learn the general distribution, right? So if a model is an expert on the data set, that doesn't really mean that it's an expert on the distribution. It's close to the distribution, but not necessarily like perfect on it, right? And more kind of concerningly is that it behaves inconsistently, right? Again, we would kind of want the behavior where like, okay, if I sample like the red points versus the blue points, they represent the same distribution, I should get roughly the same model. But in this case, no. In this case, I don't. I get a pretty different model each time I sample, right? Okay. So of course, we would want a model with low bias and low variance, right? Okay. And again, this is pretty difficult, right? Because we can solve the low bias thing pretty easily just by adding a bunch of parameters. Getting the variance low is pretty hard, right? Because that's overfitting, right? And again, just to, in case it wasn't clear, low bias is kind of the outcome or another term for underfitting. And then high variance would be what you would refer to for overfitting, right? Okay. So again, we could try to like undertake the task where like, okay, for a given data set, for a given data distribution, try to like predict the number of parameters that's like exactly perfect for the job, right? Or we could just get some arbitrary neural network, right? It might be too complicated. And then while it's training, specifically induce changes to prevent it from overfitting, if that makes sense, right? So again, a neural network might like, if just left to train, just do forward and back prop, might default to doing this. But can we kind of add some maybe loss functions or change the way the model is trained to prevent this from happening? Okay. The easiest way of doing this is just something called early stopping, right? And it's not super profound. I'm sure a lot of you have already done this before. you can notice, again, here's kind of that example I have of that line classifying our triangles, right? As you start training, right, your weights and biases are completely random, right? So it hasn't really learned the distribution. Over time, it begins to kind of split the two categories a little bit better and better until you can see at T90, it kind of learns that generalized splitting mechanism, right? The epoch 90, right? The problem is as you keep training, right? Again, like if you were to evaluate like maybe the loss of this, it would still, not be quite zero, right? So you would keep training and then learn all the, specific noise in the data set, right? And again, what is your model's objective? It's to minimize the loss between itself, right? And the data set, right? It has no knowledge of this true distribution, right? So again, as you kind of let the model continue training past this t equals 90 point, it would inevitably fit to noise, right? Assuming it doesn't underfit. Okay, so if you could just maybe stop the model early, or maybe solve or save the model state at every 10 steps, right? Uh, and then, you could just early stop, right? Before it gets to this point where it learns all the noise. So again, this is not a super complex thing, and I'm sure a lot of you have already done this before. Any questions about early stopping? Okay, sounds good. Okay, so on to something a little bit more interesting. L1 and L2 regularization, right? So let's kind of walk through another example, right? So we have a little data set here, right? We have a data set in terms of two features, X1 and X2, and we have the output Y, right? And so the true distribution is really just Y is equal to 2X1, right? And X2, which is garbage, like it's just a really like a randomly initialized column. It has nothing to do with like the true relationship, right? Of course, the model doesn't know that, right? We gave it X1 and X2. So let's say I train my neural network on using X1, X2 to predict Y. And this is what my model is, right? So I have weight 1.8 times X1. And then again, that's pretty good, right? Because I know that 2X1 is equal to Y. But then you'll notice I have this 0.78 X2, right? And again, in the true distribution, X2 and Y don't really have any real relationship. It's just because I only train on these 5 samples that the model kind of found that relationship in this small sample, right? In other words, it fit to the noise. And you'll see that the mean squared error is actually really, really low. That's pretty good. So in the model's perspective, it hasn't done anything wrong. So how do we kind of, how do we kind of deal with this? So again, just kind of go back to that early stopping kind of idea, right? So maybe just hypothetically, right, at this epoch, what is that? I'm not wearing my glasses. T equals 7, right? Maybe up until this point, the model has found that, hey, if I just change this first weight for X1, if I change this a lot, my MSE goes down a lot, right? But maybe once it hits T equals 70, this weight gets to like 1.75, right? And then 1.76. And it's noticing, it's not really getting those big boosts in performance at this point anymore, right? Then it starts tweaking 0.78, right? It starts tweaking the second weight. And then it results in a larger degree in change compared to the first one. So then after this point, right, once we've kind of exhausted optimizing this first weight, which is true, hypothetically, the model might try to fit the second weight to Y. So that kind of intuition makes sense. This is just a hypothetical, right? This is not necessarily how all overfitting to noise happens, but it's a common occurrence. Okay, so one way we can prevent this from happening is L1 loss, right? So what we're doing is we're taking the sum of absolute values of each weight across all weights W, right? So again, in our case, we then add this extra L1 loss to our main MSE loss. And then of course, we weight that L1 loss by times some parameter lambda. Why did I forget that? And lambda is usually between 0 and 1, right? And that'll make sense in a second. But the idea is we're actually like with this L1 loss is penalizing the magnitude of the weights themselves. Right? This L1 loss has nothing to do with the actual performance of the model, has nothing to do with the MSE, right? It's just that if the model, if the weights, so as you can see kind of here in the reduced loss function, if the weights are above 0, then the L1 loss will be positive and therefore the weights will be penalized, right? And so what's interesting is that this L1 loss encourages the magnitude of the weights to like decrease, obviously, right? You're penalized for having weights are greater than zero, right? And so this is really nice because it prevents exploding gradients. You're keeping your weights fairly small. And what's also interesting, and this is the main reason why people use L1 loss over L2 loss, is that the useless weights. So again, weights that like if you expect your input to have like noisy weights or sorry, noisy inputs, those approach zero, right? And so that's where the regularization comes in. So what do I mean by that? Okay, so again, this is the loss for L1, right? Or sorry, this is the loss for MSE plus L1 loss. So you take the gradient with respect to W2. Well, you get the gradient of MSE over W2. And again, this is what the gradient would normally be if we didn't have an L1 loss, right? And so this tells us, okay, how do we change W2 to minimize MSE, right? But then the derivative with respect to the L1 loss is literally just lambda times whatever sign W2 is, right? So if W2 is positive, like this derivative is just lambda, right? So what does that mean? Well, remember W2 in our case, right? It's controlling it's controlling the feature x2, right? And again, we know that x2 has no relation to y, right? They're just fitting to noise, right? And in our hypothetical, the model knows this as well. Like the model this entire time is optimizing W1. It's not really changing W2 until we get to this point where we've exhausted training W1, right? So if you consider the behavior then, so early on in training then, right? What would the magnitude of the gradient of MSC relative to W2B? Do you think it would be pretty big or like pretty small early on in training? Exactly, right? The gradient is telling you, okay, if I change W2, how much does the loss change? And let's move in that direction, right? To minimize that. Well, again, we know that W2 doesn't change loss that much, and it's exhibiting that behavior early on, right? So that would mean early on in training, this term is very small, like very small, right? Maybe 0.001, right? 0.01. Whereas this lambda term is whatever lambda is. So if we set lambda to be equal to like 0.1, right? If we sum these two terms together, the lambda, like the L1 gradient, will completely dominate this gradient, right? And what does the L1 loss do? It penalizes the magnitude of your weight, right? So in other words, just to put it kind of succinctly, if a certain weight doesn't really contribute to the loss, right? Early on in training, this main loss term will be low. This lambda term will be a lot higher. So therefore, this lambda term will squish the weight, the magnitude of the weight, and push it to zero. So that way, once we kind of reach this point where we've exhausted W2, or sorry, exhausted train W1, well, W2 is basically zero. There's nothing for us to train. Like if you were to train W2, the gradients would vanish, right? Because W2 is effectively zero. And that's what we want. Okay, does that kind of make sense? Okay. So again, in this case, the model never swapped to training W2. It's only been training W1. And the L1 lost its job, and now we have a loss that's actually higher than what we originally had. Originally it was like 0.06 or something. Now it's like 0.16, right? But that's desired behavior, right? Because that means the model has not fit to the noise of the data set, which is good, right? We're happy about this, even though our loss is a little bit higher. Okay, so L2 loss has a very, very similar concept, right? The only difference is that we're summing the squares of the gradients. Sorry, we're summing the squares of the weights, right? That's the only difference. So you can see the structure is the exact same, right? And by the way, this kind of term on the right-hand side is how you'd often see it in literature. The L1 loss would be referred to like, instead of 2, 2, it would be 1, 1, right? There's not really like an L3 loss that's well known, but if there was, and sometimes they're referred to in papers, you'd have a 3 here, right? And that would just be taking the cube instead. Yeah.
So for this and L1 loss, but like especially this, wouldn't this have a problem with like preventing weights that should be big from being big?
Really good question, right? And so that's really like that's a bigger problem with L1 loss and L2 loss, right? So that's one reason why people usually use L2 loss. Because okay, so consider so before I directly answer that, let's talk about the gradient of the L2 loss, right? Well, if we take the gradient of lambda W squared, that's 2 lambda W2, right? So again, as I said, lambda is usually between 0 and 1. So let's say I have a lambda of 0.1 and my W2 is something really small, 0.12, right? Well, my gradient ends up becoming extremely small as well. I'm not sure if you guys can see that, but that's the magnitude of my gradient is 0.024, right? So in other words, this L2 loss is barely making any changes to my gradient, right? Whereas if my W2 is really big, like 6.8, then the magnitude of my gradient becomes 4.6, right? That might like kind of overpower this MSE gradient, right? So in other words, right, you can imagine that for W like values, for weight values that are above 1, right? Those are penalized really severely, right? But for W, like for weight values that are less than 1, right? Well, a number less than 1 times a number less than 1 is an even smaller number, right? So in other words, as the L2 loss just says, okay, as long as you're below 1, maybe below like 0.8, 0.6, whatever, right? You won't really be penalized that much. This term on the left-hand side, the MSE loss, that will start to dominate. Does that kind of make sense?
But then wouldn't that be more of an issue than L1? Because if it's greater than one, it's gonna get like penalized a lot.
Exactly, right? We actually want that behavior, right? Because again, like, is there really any difference between, uh, sorry, um, sorry, I don't know where I was going. Is there really any difference between like fluctuating your weights between like maybe 0 and 1 versus like 0 and 100, right? In other words, there's enough like you can express your entire neural network in weights and stuff just through 0 and 1, maybe 0 through 2, right? Without having to let your weights get super big, right? So in other words, like this L2 loss will kind of deactivate once you hit fairly small numbers, right? But like even with a weight of 0.4, you can still do a lot. Like your gradients haven't vanished. You can still optimize very well, right? Does that kind of make sense?
So you're basically saying that it's not a problem because we want weights to be smaller.
Yes, exactly. We want weights to be small so we don't have exploding gradients for one reason. Yeah,
Okay, that makes sense.
okay. Yeah, so in this case, yeah, sorry. My computer's lagging. In this case, again, this is for the L1 loss, but you could imagine then, right? This W2 would never actually disappear. It might approach like 0.1, 0.015, but it would never fully disappear, right? Um, so, okay, and I'll compare them in just a second, but there's one more kind of very famous regularization technique, which is called dropout, right? And so in this has nothing to do with the loss function. Okay, this is more of a in training kind of implementation detail. But so again, we have this neural network, right? Just a normal neural network. And the idea is we want to randomly select neurons at every single forward pass to turn off, right? So what does that mean? Well, to turn off the neuron, we just multiply whatever its activation would have been by 0, right? So what that means is, okay, if my neural network is always outputting 0, its gradients are going to be 0, right? More importantly, its outputs to to future neurons will be 0 as well, right? So if I turn off, let's say we're looking at this layer, if I turn off these 2 neurons, well, this neuron has to try to predict the output only using these 2 inputs, right? And again, at every forward pass, we randomly select neurons at each layer to turn off, right? And again, we can control like to what extent we want to turn them off. So for example, like at the input layer, we might not want to turn anything off, right? And at the output layer, obviously we won't want to turn the output layer off. That wouldn't really make any sense, right? Um, but like, why would we ever want to like, so we're crippling our model though, right? Like at every forward pass, like we're shutting effectively, in this case, half the neurons off at each layer. Why would we ever want to do that? Okay. So consider like, we're training a model without dropout normally, right? Well, neural networks really like to put a lot of weight on a couple edges or like one edge, right? So in other words, if you can kind of see this, this neuron, it's decided to weigh this previous neuron with a weight of 4.1. Meanwhile, all its other inputs have really small magnitude and weights, like 0.4, 0.02, 0.001, right? So in other words, right, because these weights are so small, it's pretty much ignoring the inputs from these weights. And the input from this leftmost weight or rightmost weight for you guys. Like for me, what the fuck? Rightmost weight for me is completely dominating what this guy ends up outputting, right? With dropout, so sometimes it's desired, sometimes that's not, right? So with dropout, what we're saying is okay, a model that can generalize really well should be able to use all of its inputs to come up with this output, right? So if we forcibly turn off this 4.1, right, that gives a chance for the model to really like figure out how to use these other three, right? And again, the assumption with the dropout is that like, all or most of the inputs to a specific neuron are able to contribute to some extent, right? So in other words, we're assuming like, we're assuming that these guys aren't actually like noisy trash inputs, like, the previous example with X2. We're assuming that, okay, they are fairly useful, maybe not 4.1 useful, right? But maybe like, a lot more than 0.4 useful, right? Okay, and so we just want to give them the chance to contribute. That way, the model isn't overly reliant on this one neuron, right? So you could expect that, hey, if this neuron changes a little bit in our test data versus our train data, like let's say like the variation in this neuron, sorry, in this input, in the train data and the test data is like fairly significant, right? Well, that completely cripples the model, right? So by having the model think of other neurons and how to use them, it makes them a little bit more robust, a lot more robust. Okay, so we've covered kind of three very common regularization techniques. Again, L1 and L2 both kind of encourage the weights themselves to be very low. So again, this prevents exploding gradients. L1 goes a step further and like pushes useless neurons to zero, right? L2 still minimizes the impact of useless neurons, but it doesn't fully make them obsolete, right? So again, there's kind of two big assumptions we're working with, right? With L1, we're kind of expecting, okay, a lot of the inputs, either in the middle of a neural network or in, the inputs themselves, right? A lot of them are going to be useless, right? But that's a really big assumption to make, right? Like if we were using a large neural network, like, for a fairly difficult problem, like let's say we were not using a large neural network on like a really small problem, like, like we're not dumb, right? L1 would still try to zero out a lot of inputs, like regardless, right? It'd still do its best to zero out inputs. And so L2 on the other hand is a lot like less, is a lot softer than that. So in practice, a lot of people end up going with L2 versus L1 because zeroing out too many inputs is a big risk you're going to end up taking. Another reason is that L2, again, is fully differentiable because remember, it's relative to the weight squared, right? X squared is differentiable. Absolute value of X is not at X equals, where is absolute value of X not differentiable? Yeah, zero, right? So it's not differentiable anymore. So that could cause problems when inevitably the weight hits zero, right? Because if the weight's going to inevitably hit zero and it's not differentiable at that point, you have some really weird behavior. Okay, so where does dropout kind of fall into this? Like L1, it makes some pretty aggressive assumptions, but in the other direction. Dropout assumes that all neural networks, or sorry, all neurons can contribute to their, to neurons in the future, right? And that's a very big assumption. A lot of them might be useless, not like make them zero useless, but pretty useless, right? So what ends up happening is if you have like a dropout that's even like a little bit high, you might end up crippling your model, forcing it to make predictions with trash useless neurons, right? And so this can really make the model take a forever to train and make converging really hard. So in practice, people usually use L2 on average more, but again, like that isn't to say L1 and dropout are not used very often as well, right? I think the first CNN paper or the first few CNN papers use dropout extensively, right? And that's how they were able to like crush benchmarks. But okay, moving on from regularization. So before I explain what normalization is and why we do it, let's go to another example. Okay, so again, let's say I want to have like a price. I want to have a model that predicts the prices of homes, right? Based off two features, the number of rooms and the square footage or space of each home, right? Okay, so a fairly simple problem. Oh, so you can kind of see, right? if you kind of look at how the number of bedrooms impacts the predicted price, you can notice, hey, if I just jump from 2 to 3 bedrooms, the price like really increases by like 120,000, right? Like just these small changes in the number of bedrooms, like small deviations in this feature results in massive changes in the predicted price. Meanwhile, relatively, comparatively small comparatively larger deviations in square footage, right? Okay, we're changing this by like 100, magnitudes of 100, right? Result in significantly smaller changes in the predicted price, right? So in other words, just the whole, like the magnitude, the ranges of our features are completely different, right? So you might be able to guess that, okay, so again, let's kind of plot our loss landscape. So again, on each of our axes, we have our different weight values, right? And I've kind of plotted this contour map, right? And so it would best to visualize this with 3D, but I didn't want to visualize with 3D. So you can imagine that, like, if I were to like uh, see how a model with a weight of this, oh sorry, a weight combination at this point would do, right? You can imagine that it would have really high loss because region of red, right? This kind of region, this tiny little green region, is our sweet spot, right? Where this region has the perfect combination of weight room and weight space. Like, do you guys understand what's going on in this contour map? Okay, perfect. So you could kind of see though, it's like super squished, right? If we kind of travel along this W room axis, right? If we make small changes in W room, that results in like massive changes in our loss, right? Like we go from like this really red region to a really orange region. So what I'm trying to get at is small changes in W room result in massive changes, which means its gradient is going to be huge, right? It's going to have massive gradients. On the opposite side, the grade, like if we move along this y-axis, the color doesn't really change, right? Like the gradient is going to be super small. Like I can make a big step, but the change in loss is going to be super minimal, right? So again, because our W room and W space are in just completely different ranges, we now have huge gradients when we move along the direction of W room and really tiny gradients when you move in the direction of W space. So this makes optimizing, like you can, I'm not sure if you can see, but these are arrows, right? So if we kind of try to do gradient descent, this makes it super noisy, right? Because we end up kind of like, as you guys kind of, if you remember that kind of picture of like kind of bouncing around our loss landscape, right, with really large gradients, that's exactly what's happening here, but in 3D almost. We're just bouncing around our loss landscape with really large gradients, sometimes really small gradients, and it just takes forever to converge. Sometimes it doesn't converge at all, right? Okay. And of course, because we're taking massive steps and small steps, we are also risking exploding and vanishing gradient as well. So we just might not converge, or converging might take forever, and we're risking exploding and vanishing gradients just because these are on just two different scales. So the easiest thing to do is something called normalization. Now it's technically called standardization, but like most people in literature call it normalization. So what we're doing is, okay, so up this top two graphs are the original distribution of data. So you can see this varies from like 0 to like 2000, right? And we're normalizing it such that the mean, so the average value of each of the distributions is centered at 0. And the standard deviation is set to 1, right? So what we're doing is we're centering the distribution, but more importantly, we're significantly minimizing the range of the data. So now you'll notice, again, it's kind of hard to see, but the ranges of both of our data sets, I don't know why it's thin. It's not supposed to be this thin. It just rendered really weird. There was really minimal change going from this to this, besides just centering the rooms to 0, right? But you can see that the range of both of our features are now very similar. Again, they don't have to be equal to each other, but they just have to be in the same playing field, right? The same magnitude. So what happens now is that if we kind of revisit our loss graph, but with normalized data, well, now it's significantly less steep, right? Again, this is a contour map, right? As you move through colors, you're kind of going through, you're changing your height, your Z value, right? So before, like this is like you're going down a freaking cliff, right? Now it's much more of a gradual descent, right? So now you can take much fewer gradient steps because if you move a little bit in W room, you won't have a massive gradient. You'll have a well-controlled, nice behaved gradient. So just by doing this small normalization of the inputs, it makes learning go significantly faster. And is that clear why this is happening? Okay. So again, right now we're just talking about normalizing the input, right? But how, like, why don't we just kind of, so again, we're just normalizing at this layer, right? But like, why don't we try to normalize at each layer? Like we're just normalize the input neurons, right? Of the first layer. We could in theory normalize the inputs to every single layer, right? So why don't we try that, right? Okay. So the first strategy of doing that is called batch norm, right? So before I cover like what batch norm is, let's just do a quick review of what batching is. So when you try to do like when you try to train your model, right, do gradient descent, you know, you could do gradient like input a single input, or you could sorry, like send a single input through your entire neural network, find the gradient of that input, move in that direction, and then do so for every single input, right? Why do we not want to do that? Anyone? Well, what's bad about doing gradient descent and updating the model at every single input? Yeah, slow. That's one.
You can't take you the wrong way. I mean,
It could. So I think what you're getting is like you could have outliers, right? Some of your inputs might not be like, they might be out of distribution from your data set, right? They might be outliers, right? So your model in trying to optimize that might just move in a completely different wrong direction. So okay, the opposite end of that, okay, so if it's risky to do every input one at a time, why don't we pass the entire data set into our neural network and just take a single gradient, right? Why can't we do that? Like take the gradient with respect to the entire data set and then move in that single gradient direction.
Because then you would lose outliers, like ones that you want,
Um,
or like lose like granularity, I guess.
Potentially. Yeah.
it just becomes deterministic. Like you're always moving in the same direction, then you just hit a relative minimum and just hammer it down.
That's more advanced. So like what Shubes is saying is we sometimes want some variation in how our neural network approaches that like minimal loss, right? Like in trying to navigate to this perfect zone, right? We have like loss of basically zero, right? We sometimes actually like if we take the gradient with respect to the entire training data set, we would always move in this exact path, right? Obviously, right? Because their data set's the same. So what could happen, right, is that maybe like there's a local minimum on this path, and then we get stuck and we're screwed, right? Because we only have this one path to go from. In this case, like we have a super smooth, like the loss landscape is a bowl, right? But we have some local minimums in there, some saddle points, we're completely screwed, right? So we want a little bit of noise. And then so the second reason why we wouldn't do the entire training data set is it's too much data. You just can't like if you're trying to like load like an entire data set of images, like 100,000 images all at once into your model, take the gradient of that, you just don't have enough memory for that, right? So that's a more practical concern. So what's often done is you take batches instead, right? So you divide your data set into like, instead of doing one at a time or the entire thing at once, you just group it into pairs of 1, 2, 3, 4, 5, however many you want, right? So in this case, I have a batch size of 4, right? And you take the gradient with respect to those groupings of 4, right? So if you have your data set has 100 samples, right? You have 5 batches, right? Sorry, you have a data set of 100, you have a batch size of 5, you have 20 batches, right? So you do gradient descent 20 times. Now, you would hope each gradient kind of looks similar to each other, right? But they won't be exactly the same, which is good for us, right? That way we can kind of take unique pathways to that loss function so we don't get stuck. Okay, sorry, I know that's kind of long-winded review of what batches are. I apologize if you're already like familiar with that stuff. It is review. Okay, so batch norm. For each of those batches, right? And again, we're not really talking about gradients in this case. Just for each of those batches, right? In this case, batch size of 4, we normalize the activations. Sorry, it should be pre-activations relative to each batch, right? So what does that mean? Okay, I know there's a lot going on here. I realize in retrospect that this graphic was a little bit messy. But okay, what batch norm is saying to do, right? For a single neuron A, right? So I know there's like I have a bunch of like neurons here. This is like imagine this is all the same neuron, right? For a single neuron A, right, in a batch size of 5, normalize over those 5 inputs, right? So again, imagine that like, in parallel, right, at the same time, I'm inputting like, the first input, the second input, and third input into my neuron, right? And so I multiply the input by the weights and biases, right? And then I get the numbers 3, 4, 5, 2, 5, 6, whatever, right? So what I then do, and again, these are my pre-activations. I haven't passed them through my ReLU or softmax or whatever, right? Aryan, are you raising your hand? Okay, whatever. Sorry, I thought you were. What the fuck? Okay. Yeah, so we then calculate the mean of those pre-activations. We calculate the standard deviation. And again, does anyone want me to walk through how to calculate standard deviation or mean? Like, we're good with that, right? Okay, good. I would have been worried. So then we take each of these pre-activations and then we normalize them, right? We subtract the mean, we take the square root of the variance, or I guess square root of these square of the standard deviation, and then we add a little bitty epsilon term in addition to that. Anyone have any guesses as to why we'd ever add this epsilon term? Epsilon might be like 0.001 or 0.01. Epsilon is meant to be very small.
Yes.
Yeah, to avoid dividing by 0. Yeah. So again, the variance in some weird cases could literally be 0, right? Or really close to 0, right? If epsilon, I'm worried this thing's gonna like, it closes, right?
Yeah, it's probably about
Yeah, okay.
Yeah. Right, you did go back. It's about to go off within 1 second later.
Like, how do I make it not do that? I mean, that's for you guys to figure out when you lecture. This is your problem, man, not mine. Why the fuck? Ah. Okay.
But I didn't really want to leave it.
Does it work now?
Yeah.
I guess we just chill until this thing fucking wakes up.
God, I love technology.
Yeah. Oh. Yeah, nothing. All right. Play status, laptop, mine, bit. Yay. Okay, we're back. Okay. So, okay, so we normalize each of the activations. So you can imagine, after this step, all the activations are kind of close to 0, right? They don't really vary that much. They don't really vary that much anyway, but they're kind of shifted to 0. And then what's interesting is that we then multiply them by we then multiply them by some parameter gamma and add them by add some parameter beta as well. And gamma and beta are learned, right? So that's what's kind of interesting. So again, so we have our learned weights and biases, right? That learn to generate these numbers. We then normalize them, right? And then we have an additional scaling set of parameters, gamma and beta, that will scale our normalized inputs, right? So why would we ever want to do this? Well, it's, the people who proposed batch norm and later on layer norm noticed that, okay, if we always normalize this data, right, to be like, effectively centered at 0, have a very small range, right? In most cases, that helps, the model is very well behaved, right? But that also significantly limits like how expressive our data can, like how expressive neural network can be, right? What happens if we're trying to output really big numbers, right? Or we're trying to like if our final layers, like we're meant to output a really big layer, right? Well, that would force only our final layer to have large outputs or to have large weights, right? It's like now at our final layer, we would have like weights of like fucking 10, 20, 30, huge, right? And everything before that, because of normalization, would be really small, right? So gamma and beta just let you scale those normalized inputs as needed, right? And again, the same gamma is being multiplied with all of these pre-activations. Same beta is being added to all of these. Yeah.
When do you know, like how do you figure out what gamma and beta will be?
That was my question.
Well, they're learned, right? So it's
They're also.
yeah, gamma and beta are completely learned. They're not hyper.
Like during backup?
Yeah, exactly,
Okay.
exactly. So the model is kind of learning, like, okay, usually, right, gamma might be around 1, beta might be around 0, which means, okay, this normal distribution thing is working great. Let's just not mess with it, right? There are times when you might want to undo the normalization. As I was saying, like we might want to model like a large number in a specific neuron. In this case, gamma would scale it back up, and then beta would, scale it back up as well, additively, right? So again, gamma and beta almost exist to undo the normalization to some extent at certain points. Does that make sense? Okay. I think generally on average, gamma and beta lean towards 1 and lean towards 0. Okay, so they have normalized outputs, and then we just pass them to the activation as normal, right? And I know this graphic looks super hairy, right? So again, just to like reiterate, right? For a single input in the batch, right? Again, we're only talking about a single neuron here. We're only normalizing relative to a single neuron. We normalize it relative to all its other inputs, right? Going to that same neuron. So again, we have a batch size of 5. So we normalize it relative to 5 inputs, and then we output,
So I guess my question then would be like, doesn't this make it really hard to run them all in parallel because you need information from each
yeah,
batch? So
yeah.
it's like go to any given neuron.
That's a good point. Again, in PyTorch TensorFlow, they already handle that stuff. Like you can just do like import batch norm, and then it just
Okay.
handles that perfectly for you, right?
So like,
But you're right though. Compute-wise, it's weird, right? Because you have to store these intermediary values. So you have a huge batch size, then you got to store a lot of intermediaries at every single step, right? I can't remember if it slows down training relative to the next new. I think the next normalization technique we'll be covering, but as it naively without any optimizations, it would slow down training. Now, batch norm is a very old method, so I remember reading about like some ways to speed it up, but naively, yes, it would slow it down, use up a ton of memory, right? But again, they argue that this is worth it, right? Because again, we have that very smooth, nice loss landscape. And then yeah, but there is one really massive glaring issue of batch norm, which is it's completely dependent on the batch sizes, right? If you have like small batch sizes, like in my case, a batch size of 5, right, for a data set of like 1,000 values, right? Well, your means and variances won't really reflect the true means and variances of your data set, right? And so you can imagine that as your batch size becomes really big, like increases, you'll have more stable, predictable means and variances, which you would want, right? But that adds a lot of unnecessary complexity. So batch size now becomes, your neural network suddenly becomes dependent on your batch size when it wasn't really before, right? So again, so what's interesting though is that this kind of, what you would expect this to hurt the model, it actually ends up benefiting it in some really weird way. And I'll cover it in if we have time at the end. I'm about to go over, but yeah. So this behavior is unpredictable. Sometimes it actually ends up helping the model, but in general, it's like we don't want the model to be dependent on this batch size. So layer norm kind of solves that issue. We're still doing normalizations, but now we're normalizing a single neuron's pre-activation, same thing as last time, but with respect to the pre-activations of the neurons on the same layer, right? So again, we no longer care about batch size. We're only talking about a single input. We're normalizing. So again, now same graphic, similar graphic, but now like these are different neurons on the same layer, right? So neuron A, neuron B, neuron C, so on and so forth, right? And again, it's the exact same process. The only difference is we're normalizing with respect to the same input, and the things we're normalizing are we're normalizing the same feature of the same input across all layers, right? So in this case, we have 1, 2, 3, 4, 5, 6, or 5. Why did I get 6? In this case, we're normalizing across 5 values across our 5 layers, right? Beyond that, we saw our gamma and beta. We're still normalizing the exact same way, no other difference, right? The key conceptual gap here, again, like in case it wasn't clear, with batch norm, we're normalizing across each feature, across all inputs for a single batch, for a single neuron. With layer norm, we're normalizing across each feature as well. But for each neuron, it's relative to the other neurons in the same layer, right? So again, you can imagine each input, right, would have a different mean and variance and so on and so forth. Okay, so again, batch norm, as I said, becomes unstable with small batches. So I think modern day normalization papers kind of stay away from it. Layer norm has become a building block to a lot more complex normalization models or normalization techniques. But this concept of normalizing across layers is still like very common. Transformers, if you remember from last fall, they use layer norms before passing their inputs into the neural network, right? Like the classic layer norm as I described it, with no little to no changes. But yeah, okay. So last thing, I'll try to cover this fairly quickly since I got 4 minutes left. Okay, so we talked about normalization just to speed up training to help it converge if it might not have converged. Talk about regularization to prevent overfitting. Just another common problem is what happens if a model just has a ton of input features, right? I've been talking about like a input size of 2. What happens if it has a ton of those? So, well, we're forcing that first layer to be really big. So already now we're forced to have a large model, which makes us already susceptible to overfitting. And then we suffer for something called and then of course, a lot of these features might be noise or trash, right? But we also suffer from something that's a little bit more abstract called the curse of dimensionality. Very dramatic. It is pretty interesting. So the curse of dimensionality is just when your input, like your feature size, is really big, there becomes like a lot of like weird behavior in terms of how your model is optimized. Like there's a ton of weird behavior. For one, as the number of dimensions, so again, the number of features that are input increases, the number of samples you need to represent that space increase exponentially, right? So that's a huge one. And some other ones, unfortunately, I won't have time to cover, is as like mean squared error is kind of Euclidean distance, right? Like we have a point here, we're calculating how far apart they are, right? Well, it turns out as you kind of plot points in like super high dimensional space, like 10, 20, 30, so on and so forth, right? Well, the distance between those points becomes like between all those random points ends up becoming super similar. In other words, if you sample like 2 random pairs in like 50 dimensional space, the Euclidean distance between them ends up becoming like super similar, right? That's not the behavior you would get in 2-dimensional space, obviously. If I were to like get 2 random points, get the distance, those pairs would have different distances. And there's some other really weird behavior. I'll be focusing on this one since it's the most applicable. Okay. So again, so hypothetically, right? Let's say we were to try to fill up this 1-dimensional space with, let's say if I were to sample from my data set, I can confidently say that, hey, one sample can represent nearby samples that are within 1 radius of it, right? Just hypothetically, right? Well, in that case, my data ranges from -5 to 5, right? If I have a radius of 1 for each sample, I will need 5 samples to represent my entire space, right? Are you? Oh, sorry. What happens if I then scale to 2-dimensional space, right? Still about 5 by 5. Well, now I require 25 samples to match this space, right? And again, this 5 by 5 is kind of the equivalent of this 5-dimensional space in 1 dimensions. And again, as we move to 3-dimensional, 4-dimensional, the number of samples we need to represent the entire space increases exponentially, right? So what that means for us is if we have like a 100-dimensional space, right? To completely represent it, we would need an inconceivable amount of data to represent that entire space. Okay, does this kind of idea make sense? Okay, perfect. So again, we don't want to deal with that, right? There are ways to operate in high-dimensional spaces safely, right? We don't want to worry about that for now, right? If we're just training a little neural network, like we don't have to worry about that. Like we shouldn't have to worry about that. So the easy way out is something called feature extraction, right? Given these high-dimensional features, so again, like your features, you have 100 input features, right? Can we somehow map it to a low-dimensional feature space, right? And then input those low-dimensional features to the neural network instead, right? So we've actually covered like quite a few models that do this. The one that does the best, not the best, but one that you might recognize is the CNN, the convolutional neural network, right? So again, like if we could easily try to input this 1,000 by 1,000 image into a neural network, right? Just skip this entire convolutional stuff. Does anyone remember how we might input a 2-dimensional image into the neural network, which expects a 1-dimensional input?
It's like the pixel values, right? Like the
Flatten.
Yeah, flatten, right? We could literally just like unravel it pixel by pixel, like grab each pixel and just arrange it in a straight line, right? We would have a what is that? A 1,000,000-dimensional pixel space, or sorry, feature space. But we don't do that. What do we do instead? Instead, we do convolutions, right? where we slide that. Remember, if you remember, we slide that kernel, right? And we extract those spatial features. And then at the end of our convolutional layer, what do we get? Well, we get this, to us, non-interpretable, but this very low dimensional, maybe 1 by 50 or 1 by 20 or 1 by 80 space, right? Anything better than 1 million dimensions. So we now input this guy into the neural network instead, right? Does that make sense? Okay. And again, so we could kind of generalize this behavior that, again, if you've done the variational autumn code lecture last fall, this is all review from that. Does anyone remember like these slides or VAEs in general? Okay. I'll just skim through super fast then. So what we could do is treat VAEs, or sorry, autoencoders, not necessarily VAE. What you try to do is represent the input, squish it down to a little latent representation, and use that latent representation to reconstruct the same output. So in other words, you're trying to learn the identity, right? So why would you ever want to do that? Well, if you can reconstruct the output from this little itty bitty latent representation, that means, well, this latent representation represents the input, right? There's like a one-to-one mapping between the two. Each input has a unique latent representation. So you can go from one to the other very easily, right? So if this latent representation is in low dimensional space, well, it perfectly represents our input. Why don't we just train a neural network on this instead of the really big input? Seems like you guys remember how this works, so I won't cover it in excessive detail. And the last technique, I won't have time to mention it, is called PCA. Have any of you guys taken linear algebra? Okay. I'll explain it without that then. I don't know. We're already a little bit over time. The idea is for each of your features, right? We know what variance is relative to one feature, right? There's something called covariance, right? Where if you have two separate features, it measures if you modify this feature, how much do you expect this other feature to change, right? That's a little bit of simplification, but that's how it is, right? And so what you do in PCA is you construct this covariant matrix. So if you have 5 features, right, you'll have a 5 by 5 matrix. And you can just look at this matrix and say, okay, how does feature A vary with feature B? How does B vary with C, and so on and so forth, right? If you end up noticing that features A and B, have a very simple relationship where if you increase A, B decreases. If you decrease B, A increases. Well, you can almost treat them as the same feature, right? So PCA effectively identify these redundant features and figures out a way to combine them into one. So without getting too much into it, it's a non-deep method of doing this as well. Pure statistics, no weights or methods or anything. So it beats autoencoders in that regard. But yeah, okay.
Like you would just give it straight up the data set, and then it would just give you back the data set, but with less dimensions.
Sort of. It would give, so if you end up seeing that features A and B like are super correlated, right?
Yeah.
They effectively represent the same trend in data. You would learn a shared feature between the two. You'd learn how to like combine the two into a single feature, as opposed to just using feature A or feature B. Because in practice,
so that's like not like
exactly. Exactly. Like if you expect like features A and feature B to have a variance of 1, that means they like perfectly like feature A goes up, feature B goes down, or they both go in the same direction, right? In practice, it's not that close, right? It may be like a covariance of like 0.84, 0.8, 0.7, right? Pretty close, but not that close, right? So that's why we would want to combine them into like a shared feature. But yeah. Okay. Anything else? Oh, so the reason I asked about linear algebra is you do that by using the eigenvalues, but we don't have to get into that. Okay.